In section 302, you learn a lot of rules of differentiation, especially the product rule and the quotient rule, which are very, very important. You need to practice those a lot to become fluent. There are many things to use online to help you practice. StudyForge has some examples. The Khan Academy and Patrick JMT buttons that are on this website also will give you some good practice problems, so please spend some time with that. The problems I will go through here in this video won't do any quotient rule, product rule problems. However, I just picked a few problems that you might see on the assignments and tests that you might stumble on. So let's start with the first one. Find the value or values of x on the graph of f of x equals 2x cubed plus x squared minus 4x, at which there is a horizontal tangent line. So remember, a horizontal tangent line means the derivative is equal to 0. So you need to set the derivative equal to 0 and then solve for x. That's really the only thing you do here. So the product rule, I'm sorry, the power rule, said that wrong, would be 6x squared, and then 2x to the first power, and then this is 4 to the x to the first power, so like 1 times 4, and then you end up with 1 minus 1 here, you get x to the 0 power there. So there's your derivative. If it has a horizontal tangent line, it means the derivative is equal to 0. So you actually set this whole thing equal to 0 and then just solve for x. So I did that here and I factored out a 2 so that I could factor it a little easier. This is just a quadratic, factors into those two pieces. You set those equal to 0 and you get 2/3 and -1. Those are the 2 points where there are horizontal tangent lines on this graph, because that is where the first derivative is equal to 0. I've seen students do this problem, find the derivative just fine, and then plug in 0 for x. And if you think that, or if you do that, that means you're going to find the value of the derivative when x equals 0, which is not what the question is asking. They're asking you to find where the derivative is equal to 0. So that's why you make this equal to 0, the derivative equal to 0, and then solve for x. That tells you at what x coordinate the derivative is 0. And remember, if the derivative is 0, there's a horizontal tangent line at that point. Okay, next one. Find the values of m and b that make the following function differentiable. Okay, so 2 things. First is, in order for a function to be differentiable, it first must be continuous. So you do this by setting the equations equal to each other and then plugging in -1 in this case. Oh, there's a typo. That should be a -1 right there. Sorry about that. This will cause them to have the same y coordinate when x equals -1. You did this in the DBA assignment for chapter 2, which is 206. You had to make them continuous. So you set them equal to each other because they're both equal to y. And if you set them both equal to each other and then plug in the x coordinate that you want them to be equal at, then that sets up the situation where they're going to have the same y coordinate at that point. So in this case, you plug in the -1 for x, and you end up with an equation with m and b in it. You can't really do much with that. You have to stop here because you don't know what m and b are. We're going to eventually know, though, because the second part of this, in order for a function to be differentiable, it first must be continuous. Next, in order for it to be differentiable, the graph must have the same slope as it approaches both sides of that boundary line. So you ensure this by setting the derivatives equal to each other and then plugging in -1 for x. This will cause the tangent lines to be equal when x equals -1. So find the derivative of each one. This will be 4x cubed. And then this is x to the first power. M and b are numbers, it's constants. So it'll be 1 times m and then x to the 0 power. And then this is a constant. The derivative of a constant is 0. So the derivative of the bottom one is just m. So we're going to plug in -1 for x and then solve for m here. We actually have a value for m now. So m is equal to -4. If m is -4, we know this here, and you can plug that into that equation and figure out what b is here. So we have a positive 4 because the negative here and the negative 4 make a positive, and we can just get our b value, -3. Okay, our next one is kind of the same situation. We need to find the derivative and then give its domain. So the derivative is really the derivative of each of these. It's the domain part that we have to worry about a little bit. So this graph, number one, we have to make sure it's continuous. If you're going to find the derivative, you have to make sure it's nice and pretty and smooth and curvy. So we need to make sure that the points are equal to each other. So notice it's continuous because when you take 4x minus 1 and 3x squared and piecewise functions, this graph stops at x equals 1, this graph starts at x equals 1. So that's the boundary line for these two graphs. That's where one stops, one starts. So when you plug in x equals 1, you end up with the same y coordinate. So these both share a point at 1, 3, so that's good. And then this graph stops at x equals 4, this graph starts at x equals 4. So if you plug in a 4 for the x's, you end up with 48. It's a high y coordinate, but it doesn't matter. They both share a point at 4, 48. This graph and this graph both share the same y coordinate. So this one stops, this one picks up at the same place. And then this one stops at 4, and this one picks up at the same place. So it's continuous. We're good there. The derivative is not differentiable at the boundary. So the last example talked about in order for it to be differentiable, that means that the slopes of the tangent lines have to be equal at all the points as well. Now, when x equals 1, the derivatives are not equal. So let's talk about the derivative of this. This derivative of 4x is just 4. Derivative of -1 is 0. The derivative of this is just 6x. The derivative of this is just going to be 10. So you find the derivative of each piece separately. And now we have to test it to make sure that the derivatives are equal to each other at each boundary point. So 4 equals 6x, plug in the 1, those are not equal. And then 6x equal 10, plug in the 4, which is where those two meet up, those two are not equal. So when you do the domain of our derivative equation, we cannot include the boundary lines. Like notice here, we have equal to, equal to. We're allowed to let them equal to each other because they're continuous. Here, we can't let them be equal to each other because the derivative does not exist. So the derivative exists for all values except for those boundary points. So our domain would be all real numbers except for 1 and 4.